The dollar dilemma. In life, opportunities pass and go. This new exciting house on the market, but there might be an even better one in the future. Or there's this new job offer that I have, but I'm not sure if I should take it. Or wait for a better offer in the future. You don't want to choose too early or too late. How do you decide when to choose at the right moment and when to settle down?
Well, by employing optimal stopping theory, your chances of picking the best option will always be no less than about 37%. But first, what is optimal stopping theory? Optimal stopping theory says that in order to pick the best option within a given sample of options, you should first get a sense of the sample, or what you've got to work with, by rejecting the first 37%, or 1/e% of options, then commit to the next option that's better than all previous options. But why do we have to go through 37%? How did we derive that value? Well, let's write a two-variable function p using two inputs. R will represent how many options we first reject, and S will be the total sample size. Probability of R, S will represent the probability of picking the best option if we input R and S. We should try to find the values of R that maximize P of RS to have the greatest probability of picking the best option. Let's call the best option B. Here, we should note that PRS is the probability that you pick B. The best option is equal to the sum. Because of this formula right here, if A and B are mutually exclusive, then probability of A and B is probability of A plus the probability of B. Also, remember that B can be anywhere in your sample. It can be the first option, third option, fourth option, 15th option, or the last option. Thus, the probability of picking B is equal to the probability that B is the first option you get and you pick it, plus the probability that B is the second option you get and you pick it, plus the probability that B is the third option and you pick it, and so on and so forth, all the way until plus the probability that B is your last option, the Sth option, and you pick it.
Let's calculate the probability for each of these scenarios. Well, if we use optimal stopping theory and we reject the first R terms, if B is among the first R terms, we're going to reject it. Therefore, the probability of the first R terms in the equation above all equals 0. After you've gone through the first R terms, if B is the R plus 1th option, you're in luck. Because it's better than all of the first R terms, you're going to pick R. The probability of B being the R plus 1th option is 1/S. B is just as equally likely to be any of the S possible positions. If B is the R plus 2nd option, you'll pick it unless you've already stopped at R plus 1 because it was better than all of the previous R options. So we can subtract the probability that we already stopped at R plus 1 from the probability that we select B if it's R plus 2. Now there's a 1/R plus 1 chance of that happening. Because there's a 1/R plus 1 chance that out of all R plus 1 options, the last R plus 1th option was the best, so the chance of this not happening is 1 minus 1/R plus 1, which is just equal to R/R plus 1. The probability of the B being the R plus 2nd option is 1/S. So B is the R plus 2nd option, you pick it, is R/R plus 1 times 1/S, which is R/S times R plus 1. Continuing this logic, we can find that B is the R plus 3rd option and you pick it, equals R/S times R plus 3. And that B is the S option that you pick it, equals 1/S times R/S minus 1, equals R/S times S minus 1.
Adding up all of these individual parts, we can get a sum like this. We can factor out 1/S and R from the right side to get this equation. Now that we have this equation, remember that we want to maximize P of R, S, the probability of picking the best option, and we want to choose a value of R to maximize P. From this sum, we can write two equations. P of R minus 1, S is less than P of R and S, and P of R plus 1, S is less than P of R, S. What does this mean? Well, we want to maximize P of R, S. If R was one number less, if it was R minus 1, we'd stop rejecting too soon, and we'd have a lower probability of picking B. If R was one number greater, R plus 1, we'd stop rejecting too late, and we'd also have a lower probability of picking B. For instance, out of 100 slips, the probability of picking the best option out of the first 37 slips is greater than if we stopped after 36 or 38. Let's solve for each of these equations. For P of R minus 1, S is less than P of R, S, we can substitute inputs R minus 1, S and R, S into the sum we wrote, like this. We can cancel S from the denominator from both sides, and we'll be left with this. We can distribute the first term on the left side to equal 1. Now we can see that both sides have a common factor of 1 over R plus 1 over R plus 1 all the way to 1 over S minus 1. Now, we can subtract both sides by the right side of this equation and bring everything onto the left. The difference is 1 minus 1 over R plus 1 over R plus 1 all the way to 1 over S minus 1. Add 1 over R plus 1 over R plus 1 all the way to 1 over S minus 1 to both sides, and we'll get our bottom equation. The same logic can be used to prove that P of R plus 1, S is less than P of R, S. So, we can write this inequality. If we use a computer, we can see that if we increase the value of S, the value of R approaches 1 over E, or 37%.
Our product is a board game called The Dollar Dilemma. It is a multiplayer game about making economic decisions, where players can get jobs, buy up property, and invest. The board game looks like this. Players start here on the start square. Each player starts with $100,000. Then each player will take turns rolling a die and will move however many spaces indicated by that die. Players will place their game piece on whatever square they land on to indicate their spot. If you land on a color square, you have an opportunity to earn money. Your task is to make the best financial decision using optimal stopping theory. For instance, let's say that you land on buy a house. If you take the offer, the game master will show you a bunch of houses that are on the housing market. After you reject a house on the market, you can't retroactively go back on your offer. Your task is to stop and purchase the best house you think you've got. As you can see, using optimal stopping theory will be extremely strategic here to help you make the best purchase. Players should go through the first 37% to get a sense of the scope of the market and then pick the next best house. The same goes for when players purchase a car, make investments, or take up job offers. If players land on education, they can get an education. Some of the jobs' paper slips require players to have an education, so having an education can be expedient for the player. After you made a purchase, you keep the card. If you land on a pink spot, you lose money and need to pay. For taxes, you lose 20% of all your money. If your car broke, you need to pay 50% of all your money. Every time you land again on one of your spots, investments, job, house, you gain the amount of money specified on the card. If you buy a house, every time you land on that spot, you get more money. If you land on chance, you roll a die. If you land on an odd number, you earn $50,000. If you land on an even number, you lose $50,000. Players lose if they got into debt. After a set amount of time, the player with the highest net worth, cash, and assets wins.
This mirrors the real world. In real life, you'll be presented with many, many opportunities, and you can choose to take them or reject them. And for those opportunities, like the job market or housing market, where you don't know the full scope of all of your options, your best bet is to use optimal stopping theory.